Okay, so let's look at changes in allelic frequencies, or what causes evolution. So one of the things that can cause evolution is all those Hardy-Weinberg assumptions just flipped around. So a mutation can cause evolution. Mutations are going to provide new alleles. This is the raw material for evolutionary change. Now, we always refer to mutations as being harmful, but as I said before to you guys, the differences that we see between each other are mutations that have stayed in the human population. Next is gene flow. Gene flow increases variation by introducing new alleles to a population. But one of the things that can happen with gene flow is if you have continual gene flow between populations, that's going to make those populations genetically similar, and that actually prevents speciation from occurring. And so this is why the human population is 99.9% the same, right? And that's due to the continual gene flow that has occurred between populations. Let's look at some non-random mating. So some non-random mating, these are where individuals pair not by chance. And one of those is in inbreeding. And so inbreeding is a mating between relatives, and inbreeding isn't all that common. Most animals try to move away from each other, but it can occur. And one of the problems with inbreeding is this increases the proportion of homozygous individuals in that population. All right? And a lot of recessive genes can be harmful genes. And so this is why most organisms try to avoid this. All right? So this is not showing inbreeding. This is showing sexual selection. Sexual selection is where females choose to mate with males that have a particular phenotype. So what happens in here is that we have an energy imbalance. So the female produces a lot more energy in the development of the offspring. I think I might have mentioned this to you guys before. But she is not only going to produce the egg cell, which is larger than a sperm cell, she's also going to produce the yolk, and the ovalbumin, and the egg shell itself, and she's going to lay that egg, and then she's going to take care of the eggs until they hatch, and then she's going to take care of the offspring until they are ready to live on their own. This guy, all he provided was some sperm. So it's a huge energy imbalance here. So what she wants is the best genes that she can possibly get. And so she's going to mate with the male who she thinks has the best genes. And for peacocks, it's the males that have the most eye spots. And he's saying he has really good genes because he can look like this in that environment and still survive. And those are the genes that she wants because it's going to give her offspring the best chance for survival. So this is why you see peahens looking more drab. They blend into the environment. And these guys looking much more colorful because she's going after those best genes. And it doesn't matter that her friend Martha just copulated with him. She's going to get those best genes too. This also leads to what is known as sexual dimorphism. And that's where the sexes look different from each other. Now let's look at genetic drift. So genetic drift, as I mentioned, is a change in allele frequencies due to chance. In general, this can affect smaller populations more than larger ones. All right? So, what can happen sometimes is a rare phenotype may not get to reproduce. And how it affects smaller ones, because, as I mentioned with the flip of a coin, if you have more coins to flip, the less chances that, the more times you're going to get something that you would expect to have an average. You flip a coin 10 times and get 10 heads, but if you flipped a coin 100 times, it's very unlikely that you're going to get 100 heads on that. All right? So, a couple of events here that can really affect genetic drift here. One is the founder effect, and this is a change in allele frequencies of a population resulting from the isolation of a smaller group from a larger population. All right? So here, there are a few individuals to start that new population, and so it only contains a fraction of the total genetic diversity of that original group. And so what we can see in some groups here, and this is showing this polydactylism, all right, and even though I don't think any of these people are Amish, it's very common among the Amish of Pennsylvania, and that's because they have a small close-knit community. Another thing is a bottleneck effect. So a bottleneck effect is a change in the low frequencies of a population caused by a sudden reduction in the population size. And so that sudden change in that population size reduces the variation. So this is a slide I like for this. We have a lot of variation in the population. We have a bottleneck event that occurs, reduces that population. So even if that population comes back to the same levels it was at the beginning, we've lost that variation. It's going to take us a long time to get that variation back again through mutations. All right? So it greatly reduces the genetic variation in that population. Things that can cause this are natural disasters, diseases coming through here, even overhunting caused by humans. All right? So let's look at natural selection and types of natural selection. And the first is called stabilizing selection. This is natural selection that favors intermediate types over extreme types. So what you see here is that these on the edges, they are selected against. They don't survive. And so this curve gets narrowed up as we move along. All right? And so an example of this is human birth weight. As you can see here, you know, most of these kids are between 6.5 and 8.5 pounds, and then we have some extremes on the end. All right? So prior to modern medicine, this graph got narrowed up here because if you're born too small, well, you weren't fully developed and you didn't survive. If you got too big, well, you had complications with the birthing process. All right? Now modern medicine, we can get babies much smaller than this, and we can get babies much larger than this. The largest baby ever born was 23 pounds. So, next is directional selection. This is natural selection that favors one extreme type over another. All right? So what happens in directional selection, and this is showing it here, is that one side is selected against. And so that's going to shift the curve in one direction or the other. All right? Now we did this with turkey breasts. Right? We selectively bred for larger and larger breasts of turkey. This has occurred naturally with horses. This horse size has increased over time. That's an example of directional selection. Cranium size in humans is another example of directional selection. Here's an unfortunate directional selection. When we use pesticides or herbicides or even antibiotics on bacteria, we are selecting for those organisms that can survive that. So it's going to kill off most of the organisms, but a few, just due to random variations in that population, are going to survive, and they're going to pass on those resistant genes to their offspring. And that's an example of directional selection. Lastly is disruptive selection. This is natural selection that favors extreme types over intermediate types. All right? And so what we see here is that middle is actually selected against, and only the ones on the edges are really going to survive. We actually see this with male bluegill. Male bluegill typically are territorial males. This is a territorial male here. And what they do is they make a nest, essentially a depression in the bottom of the pond or lake or stream or wherever they're living, and they entice females in there, and so the female will come in, and the female will lay eggs, and the male will lay sperm on top of it. They have external fertilization there, all right? This guy right here is what is known as a sneaker male. Sneaker males are about the same size as females, and they look like females, and they behave like females. So what's going to happen here is while this guy is breeding with a female, a sneaker male will come in, and he'll lay sperm down on top of her eggs. All right? So this guy doesn't chase this guy away because he thinks it's another female coming in to lay eggs. And why would he chase a female away? Because if he's chasing a female away, he's going to lose fitness. Unfortunately for him, he is losing fitness. He just doesn't know he is. And so what this creates is two situations with male bluegill. You have large territorial males, and you have these smaller sneaker males. Any males in between are too large to be mistaken for a female, but they're not big enough to hold a territory. So even if they make a territory, a larger male will chase them out of it.